Okay, morning again, everyone. So we're going to be doing a few questions in OpAmps. As I said, I will start you all up on them. Parts that you really need assistance with, or that I foresee you will need assistance with, we will go through in depth. If not, it's just going to be really quick sailing through with the questions. So if you all have any questions, make sure and put up your hand or ask. It's just a few of you all, just 7 of you here in the room. So let's see what we have here. Again, these are all past paper questions. Do not ask me which year because I didn't write it down or I didn't save it. I think. Did I? Yeah, some of them have years. All right, so we can get some in years. All right, so let's see. We have 2005 paper. This could have been paper 1 or paper 2. I didn't write down which year it was. I should have. All right, so let's read the variation of the gain on an inverting amplifier at different frequencies may be investigated with the circuit as shown in figure 3. The input and output signals are displayed on the screen of a double beam cathode ray oscilloscope. Double beam meaning we can show both X and Y components in your output. So the input is provided by a signal generator. Signal generator is simply something that gives us an input signal. All right, so we get your wave for your input. So let's look at our diagram here. All right, just learn to appreciate what we have in front of us and let's see what we have. So number one, we can see that we do have an inverting amplifier because the question did say it's inverted, and we're going to our negative input. We have our input, we have our output, we have our feedback resistor being RF. Oh, that's a big marker. All right, so feedback resistor here is RF, and RF is equal to 1,000 kilo ohms is basically 1 mega ohm. Well, here just have to compare your values. And if you look here, our input resistor is 10,000 ohms. Our source voltage is plus and minus 9 volts. So first thing they're going to ask us, what is the gain of this amplifier at low frequencies? So we want to get our gain, and our gain here is going to be, how do you get gain of an inverting amplifier? All right, your gain is just going to be, all right, AV is equal, now this is a closed loop gain because it is a closed loop amplifier. It's just going to be minus RF over RI, which is 1,000 over 10. Remember, the k's will cancel each other and you get 100. Simple, that is worth 10 marks. All right. So the next part, at higher frequencies, the gain may be lower than this theoretical value. It can be measured by use of a double beam oscilloscope here, right? Figure 4 below shows the output trace and the input trace at a higher frequency. So this is basically what you're just looking like, right? When we look at our in and outputs. The gain of the setting of the CRO is set for 1 volt per division. So that means we can read our graph or read our screen and see what our output is going to be, what our values are. So 1 volt per division, as in per division, 1 volt. All right. Please note you have subdivisions and you have regular divisions. In this case, the division is between each main value or each main line on the screen. All right, so let's see. So here we have our output and we have our input. So let's just break this up so you all know what in the screen you all should be looking at. So let's just take a line here. This is showing both your input and your output together, right? So our input, right, even though it looks negative, it's just one will be the reverse of the next because we are in an inverting amplifier. So this is our input, all right? And if you look at your input, we're going to have a plus and minus voltage of 2 volts. Well, of 1 volt. We have 1 volt at the bottom here. Oh, that's a big thing. All right, so we have 1 volt at the bottom. Why? All right, so we have 1 volt here, minus 1 volt, and we have plus 1 volt at the top. And if you look here, you will see that your voltage for your output is not as large as your input. Now remember, it's not supposed to be as large as your input because it has your feedback going on. And anytime your output voltage starts to reach your, oh no, it's a big division, right? It's actually got bigger value because if you look here, the output is set for 1 volt per division while the input trace is 10 millivolts. So that means this is 10 millivolts and 10 millivolts. My apologies for that. All right, so I have 10 millivolts here, 10 millivolts here. How much is a milli again? So this will be 1 by 10 to the minus 2 volts at the bottom, and then you're going to have 1 volt, 1 volt. And that actually goes along with the question that we just did because it says using the theoretical value, right? If our gain is supposed to be 100, just so you know, this is how you learn to look at your question and check. Don't just take numbers and run with it just so. If your gain is 100, right, and my input is 0.01 volts, then my output should be 1 volt. Everybody agree with that?
Yeah.
Yeah, right? So we know the theoretical or the biggest output we can get from this amplifier has to only be 1 volt. And by looking at the top here, you realize we don't get 1 volt for our output, which is good because if we start getting a really large output, we will go into what? Anybody? What happens when we go to a very large output for your amplifier?
S-
Starts with S.
I forget.
I forget.
Sta-
I forget it's not a word that starts with S.
Mr. Get saturation.
yeah,
Saturation, that's what we're talking about. Right? And what happens when a circuit gets saturated?
it is go back to the original voltage or something.
No, it just shuts down.
Uh,
It doesn't amplify the circuit and your signal anymore. So it just essentially stops working as an amplifier. We're not saying it shuts down the circuit as in destroys the circuit. It doesn't work anymore as a circuit, as an amplifier. So let's look and see what our output will be, how much our output will be. Now they said that each one of these here is 1 volt. And it's broken up into 1, 2, 3, 4, 5. So that means each small line will be 0.2. Now let's read what our output voltage will actually be. All right, see, this is why you need practice in this question so you can see what your actual output voltage. Let's read what our actual output is. All right, so we're going to have 1 volt, 1, 2, 3. So you're going to get 1.6, which is equal to 0.8 volts for your output. I am waiting for anybody to ask where I get 0.8 from, or you all figure that out. Anybody? You all figure out why I got 0.8 and not the 1.6?
No.
Why would I
Because of a
use
double beam.
a double beam? Simply says that it gives us the both input and output in one reading. But why do you think I am reading 0.8 volts as my output as opposed to 1.6?
Miss BK, half the 1.6 in the graph.
Right. I have the 1.6 in graph. Remember, this is an AC signal. And an AC signal usually looks like this, where it goes through your zero, right? So at the top here will be your plus max, and the bottom will be your negative max. It's just because how the graph is or how the line is drawn here, it just gives us our signal trace. It doesn't really tell us, it's supposed to be giving us plus or minus. We are supposed to take the knowledge that this is an alternating supply, that we are rapidly flipping through positive and negative cycles, that we do have a plus section and we have a negative section. Everybody understand? That makes sense? Yeah? No? Yeah? Not talking like a crazy woman? Well, I do that anyway, but still. Yeah, you all understand where I'm coming from?
Yeah, Miss, I understand.
Good, great. So that's how we end up getting the 0.8 volts. Now this would have really, really, really tied up churn. I can imagine if we were in the correcting room for this, we would have been, no, that's just messing up the churn. Right? But let's take into your mind your actual fundamentals about how things are supposed to be, rather than taking them for face value. Right? This is where all the trick questions are in this topic. So now that we've seen that, let's move on. This had nothing to do with the calculation. It's just to look at your question and see how to break up things. All of that. This is the wrong graph. Log of A. What does come from? I don't know. Let's read. Continue reading. What is the gain of the amplifier at that frequency? So that means we're going to look here. We know our input is 0.01 volts. If you all can't see that marker enough. Right? Our input is 0.01 volts. And for our output, we got 0.8 volts. So I want to now go and work out what is my gain. Remember, gain here, minus RF over RI. Now, remember, we will have a negative sign. And this negative sign actually does show itself in the graph, because look at it. One of the graph, your input is now completely inverted to give you your output. So that means the negative sign works out itself there anyway. So we can just take out the negative sign. All right, so I want to work out my gain. It's just going to be my, or it's going to be my output over my input. And what was my output? 0.8. And what was my input? 0.01. And I get a gain of 80. All right, so the gain here is actually less. Why this is 3 marks? Because they needed you to go into the graph and be able to identify that that your signal swing, even though your signal swing was 1.6 volts, we needed to know how much was the amplitude of your wave, or the amplitude of your signal. And this here, it would have been half of the 1.6 to give you 0.8. All right, now just to check, all right, if I had used the 1.6 instead of the 0.8, let's see what we would have gotten. We would have ended up getting, right, suppose your VO was 1.6. Then that means your gain in this graph would have been 1.6 over 0.01, which is 160, which is bigger than what this circuit is capable of providing. Because what is the gain of this circuit? The gain of this circuit is 100. So that is how, if you had used the 1.6, you would have gotten the question wrong. Right? So this is where the very simple equations, very simple mathematics, But here you just have to be a little cognizant of how things are supposed to work. Everybody understand everything there, where the trick in that question was, right?
Learning.
You saw what the trick was?
Nah, miss.
Anybody want to explain what the trick was in that question? Because I want to hear your own words, so that means that you understand it. Anybody?
With the alternating current.
Mm-hmm. Why? Okay, let me see if I could get you to explain this properly. All right. The trick in this question was to be able to identify what the actual output voltage was. All right, now here, a regular student would have just gone and read off the graph, plain and simple. All right, let's see, read off our graph. If we had read off our graph, I would clean up the whole page. Start from scratch. All right, starting from scratch. And again, you'll see how easy questions are once you learn to pay attention to them. So they said that the output is 1 volt per division. So that means that from here to here is 1 volt. And input trace is 10 millivolts per division. So that means our input trace is 10 millivolts, 10 by 10 to the minus 3 is equal to 0.01. I am jumping that maths, hoping that you all know how to do that maths quick. All right, so each one here, look at the difference. So I want to know that my input, if my input was 1 volt, now my input voltage will be 1 volt because I have an alternating supply. Let's cut this off up to a place where you will understand where the graph starts from. Suppose I had started my graph here. All right, let's just say we started the graph from here. Okay, that was the stupidest straight line. All right, we are imagining that our straight line starts here, our y-axis starts there. Okay, and it cannot go get straight. Right, so let's just imagine this is our y-axis here, right? And we know that our graph is running up and down, right? And to get your signal, it has to be, we will get our Vmax positive. This is looking at currents and voltages, and our Vmax negative. It is not this entire wave. This entire wave is not the amplitude of your alternating current. Your alternating current rapidly switches from positive to negative. And by switching from positive to negative, there is a point where it is 0. So we just cannot take this entire value here as the amplitude or the value of our alternating current. We have to break it up into 2 because that is how our alternating current works. All right, so let's try this now. All right, so you can count it and see that our alternating current, or no, our input, where's my pen? Pen disappear, okay. My input would have been from here to here. This is my positive signal at the top, and my negative signal, when it rapidly reverses, is at the bottom. Similarly, my positive signal for my output would have been this section, which is half of the wave. I'm trying my best to draw it half. And my input, or my negative section would have just been this bottom part. Because remember, as an alternating current, we rapidly flip back and forth from positive to negative. So my V in, which is 1 whole division, is 10 millivolts or 0.01. So that is our input. We know that our V in is 0.01. Now I want to read my output. They said that my output is 1 volt per division. Let's zoom in here and get a wee bit closer. Well, a lot bit closer. All right, so I want to read my output now. My output, my entire wave, which is my positive and negative swing of my wave, is 1. Then we have 1.2, 1.4, 1.6. So my entire wave is 1.6 volts. That is not the value of my alternating current, because my alternating current is going to be half of that value, which is going to give me 0.8 volts. So that's how I can say that my V out will be equal to 0.8 volts. So the trick here was to learn to split your thing in half, or there was another way you all can do this, but it would have been wrong. We could have used our V in if you had read the entire wave. So suppose you had gone and read the entire wave now. All right, you would have gotten the same results, but the method actually would have been, all right, if you had taken this entire input wave, if your entire input wave would be 2 volts, because we said that each division is 1 and 1 volt. And if you look at your output voltage, all right, our output, our entire wave swing for our output is 1.6. Now these two will work out to do the same thing, because 1.6 divided by 2, all right, under these 2 millivolts. All right, it would have worked out to give you the exact same thing. So this is where you have to learn to break it up into either one. Now, personally, I would have accepted this much better, knowing that you have identified that we do have an alternating supply, and we do not take the magnitude of the entire wave. We have to take the magnitude of half of the wave. Sorry, I don't know why I did that. But either way, you would have gotten the same value, because I just check here. If I wanted to get my gain, it will have been VO over VI, 1.6 over 2 by 10 to the minus 3, and you still end up getting 80. Check it on the calculator, tell me if you end up getting 80. No, 20, my apologies, 20. This is 20. Each one is 10. You all got 80? Anybody working it out? That's 1.6 divided by 20 to the minus 3. Ah, well, moving on. All right, so when you take your value of your graph, right, if you get your gain to be 80, that would be correct, because the gain of your voltage, the gain of your amplifier cannot be larger. All right, the gain of your VO over your VI will not be greater than your closed loop gain cannot be larger than your open loop gain. And your open loop gain, all right, so you cannot have it that much larger. It will not work out that way. So moving on page 8, which is this page here, this is page 8, shows data collected in such an experiment. Use the graph to complete the table. So you've been given log of your frequency in hertz. So you all are supposed to now go ahead and read off log A from your graph. So you're going to print it out and do it yourselves. All right, so if you just want to start up, let's just start this up and so let's flip this graph. This is annoying that it's on this side. See, actually, it was lazy. Somebody didn't want to flip a graph page. Or somebody probably didn't know how to flip a graph page. We should stop being so mean, and they don't know how to flip a paper. All right, so if that is our graph, and they want us, we have our gain here. All right, so we have log of A, and then we have log of our frequency. Remember, for bandwidth graph, it's supposed to look like this, where we have our frequency on our X, and we have our gain on our Y. But why are we using log? Log indicates that we probably have very large numbers to deal with on our axes. So to make life a little more simple, as in it's really simple to work with ones and twos, as opposed to go and work with 15,000 and stuff. So that's why they use log. But when you're using log, remember to go ahead and convert this back, which is why they have it on the table. So what's the first value? Let's go ahead and read down the first value and see what we get. Sorry if you get, so you want 2, 3, 4. So let's see where 2 is. Log, hello. Okay. All right, log of 2. 2, log of 2. Oh, we want, so you want log of 2. So you're going to go up and you're going to read across at your log of A will be equal to 2. Then they want us to find 2, 3, 4. So you want log of 3 will also be 2. Log of 4 will be about 1, 2, 3, 4, 5 to 1.93. All right, so log of 4, all right, will give us 1.93 because you read, sorry, you're reading across and then you had 1.93. All right, between 2 and 4. All right, log of 4.5, so you want 4.5, 1, 2, 3, 4, 5. You want in the middle here. We get our intercept, so that's about 1.1675, 1.75, and so forth. So you just put in your values in your table, right, and whatnot. So let's see, we can use 22193. So you can get 22193.175. So you go ahead and do anti-logs, hit anti-log on a calculator. All right, so anti-log of 2 will be 100. All right, so you'll have 100, 1,000, 10,000, 4.5, 31,000, 62, something. All right, so you just put in your values, work it out, hit second function, log on your calculators. All right, second function of 1.93. All right, 85. Now this is supposed to be getting smaller because your gain will decrease as your frequency gets larger, and we have said that because your frequencies are pretty small, your gain is small when your frequencies are small and very large. So you complete your table. Oh, Jabari is coming in. Right, and whatnot. So you want to find the bandwidth of the amplifier. How do you find the bandwidth of your amplifier? Right. All right, for 1 mark, you want to find your bandwidth of your amplifier. Here you're going to look at if your gain, your maximum gain is 2, right? We find our bandwidth at gain over root of 2. All right, so we find gain of root over root 2, and then we go ahead. So this will be 2 divided by root 2 is not 1.4. Yeah, 1.4. Actually, that is very wrong thing. $1.8. All right, so the gain will actually be 5, 6, 1.8 something. And you read across your frequency. So you go from a frequency of 1 to the frequency of 4.4. I'm waiting for a question. A real obvious question. Somebody tell me, if my gain was 2, what will be my a over root 2 if my gain is 2?
$1.4.
1.4. Now, this is where you can make a little mistake. This here tells us log of A. Log of A is not equal to A, because let's look at how our values will work. If our, all right, that's why I was a little surprised that that's just worth 1 mark here, but yeah, all right. We can see log of A max here is actually equal to 2, but A max will be the inverse log of 2, which is 100. So my actual gain is 100. And I want to now go and find my root mean square of 2 of my gain. All right, because that is how you get your bandwidth. You find your bandwidth by finding the intercept of your board plot with your gain over root 2. So here, let us divide both of them and see what we'll get. 2 over root 2 will be equal to 1.4. Let's look in and see how big the difference will be if you had used the plain value from the page. And in this case, it'll be 100 over, let's use a brighter pen, you can see. All right, gain over root 2, and you would end up with 80 point something or 70.7. Doesn't. Wow, I'm sorry. All right, so I end up with 70.7. Now, if I had worked out the gain of the log, let's see if that would have been correct. If I had found the root mean using log of A, I would have gotten 1.4. But that means the log of A over root 2 would have given me 1.4. That is not what I want for my curve. I want to get which point here is intercepting my lines. And if you go ahead and find anti-logs or inverse log of 1.4, you would see you would get a much different answer. You would end up getting, if you had gone and found 10 to the 1.4, because 10 to the x is equal to log to the minus 1, in case you never looked at your calculator properly. All right, and you'd end up with 25. Look at the big difference. And log, right, doesn't, this is why we need to convert our values back to plain decimal values before we do any sort of division and conversion. Everybody understood why I went and found actual A and did not use log of A. Or do I have to go over the whole thing? Let's go over the whole thing. All right, one more time. This is why in the notes I said when you use log, care must be, okay, chat. Right? If you notice, let me see if I pull this up from the handout. Stop share, open share in your full OpAmps. If you go back to our handout, you are going to see that frequency, well, not just frequency, anytime you use a log scale, care must be taken to do proper conversions. Now, frequency is very, very, very frequently, don't want to sound redundant, but frequency is usually noted or written in the log scale because we get very large values. In this case, they decided, hey, if we have a log graph, let everybody be a log graph. So what they did, this still applies, right, to the y-axis because it was a log scale. So we always must take proper care to convert our values before we do any sort of calculations. This is where the question goes from being very simple to, wait, watch it properly. All right, so things to remember the back of your head, how alternating currents move, how to use and approach log graphs and scales. We cannot just use them just like that. So let's return to the question now, knowing that, OpAmps. All right, and let's try the question again. They have asked us to find the bandwidth of this curve. All right, now bandwidth of this curve is where we get, okay, that is too, well, all right. Scroll across a little bit, make you a little smaller so you can get some writing paper. All right, bandwidth is equal to FH minus FL. And where do we get FH and FL? FH and FL are the intercepts of your graph of AV over root of 2. That is where we get our FH and our FL. So our FL will be right here since we don't have it. And our FH will be in this spot here. All right, so this will be FL. All right, since we're taking it at this point here. And we will get our FH. Or in this case, we can just read our FH value. So now that we know what we have to read off, we're going to see what we have. Now using, as I said, anytime we have log, care must be taken to convert our values to regular numbers. It is easy to convert here, but our big trick, they snuck it in, they're really, really sneaky. They gave us log of A. We have to convert this also. So knowing that, and it's easy to do, if I know if log A is equal to 2, then that means A max, this is still A max, right? Because this is the highest value that A got, will be the inverse log of 2, and the inverse log, if you just want to write, log to the minus 1 is just 10 to the x. So if I want to find inverse log of 2, it's just going to be 10 to the 2. Real easy. That's why I could have done it mentally. All right, and 10 squared is 100. So that means the maximum gain of my amplifier was not 2, it was 100. So now I want to work out what is my root mean gain. My root mean gain is going to be my gain, not my log gain. Trick, very tricksy. All right, if I have to quote Gollum, and I will quote Gollum. All right, it will be gain over root of 2. So if I have to work out my gain now, it's just going to be 100 over root 2, right? And I get 70.7. So I know that my root mean gain is 70.7, but I don't have 70.7 on my graph. What does my graph have? My graph here labels log of A. So guess, why does it keep doing that? So what do I do from here now? I have to now go and find log of 70.7 to find this section here on my graph. So I find log of 70.7, I get 1.8 something. $1.85. So I read off 1.85. 1.85 is what I am going to be reading off from my graph. So I look for 1.85 because 1.85 is on the log scale. All right, so let's just erase this. I look for 1.85. Okay, it's a little higher value. 1.5, 1.6, 1.7, 1.8, 1.85 is the middle. All right, so this will be my FH. I just read it down. Okay, that's really poor reading. All right, and my log of FH is equal to 4.23. All right, so if my log of FH is 4.23, then I could go ahead and read off my FH as finding anti-logs of 4.23. So FH will simply be 10 to the power 4.23, and you end up getting 15,000 or something. Or 16,000, 17,000. You can round this up to 17,000 hertz. Everybody understood what went on there now? Where the little trick was? I think it will help to actually go and work it out yourselves and you understand. This is why I like to do questions after you all have done them. So your brain kind of wrapped around it partially. All right. Even though it's a really loose loop and it falls long as soon as you touch it, that's all right. A loop is a loop. So going down. So you would have gotten the bandwidth of the amplifier. All you had to do now, sorry, let's just scroll back up, was to read off this value at the top here. Now this would have given you 1. You find your FL is equal to 1, right? Your bandwidth is equal to FH minus FL. So this is where you had to convert this, go back and convert this to regular decimal numbers, not log numbers, to get your subtracted value. All right, so please, you have to remember to convert this. Anti-log of log 1 would end up giving you 10. So in this case, still your bandwidth is essentially 17,000. Because 17,000 minus 10 is going to give you 16,990. Basically 17,000. If you had to round that up in standard form, 17,000. All right, so bandwidth, there's a D in there somewhere, is equal to 17,000. So reading down, who is still messaging me? Why? Okay. The value of the input resistance Ri is changed to 1 kilo ohm. It was 100 kilo ohms before. Remember, Ri was, no, it wasn't 100. It was 1 kilo ohm before. And 1 kilo ohm before gave us a gain of 100. That is what the question was at the top. Now they are asking us if we had taken the input resistor and dropped it to 1 kilo ohm, how low will the frequency be and the gain, how will the low frequency gain and bandwidth of the amplifier change? So what we can work out now, we're going to realize if our input resistor is now 1 kilo ohm, our feedback resistor was still 1,000. So that means our gain is going to be 1,000. So our gain will increase. And how will our bandwidth change? If our gain was 1,000, let's just read here. All right, if our gain was 1,000, we would have ended up getting, let's just use some imagination here. Sorry. All right. 1,000 means if we take log of 1,000 is 3. So that means our graph would have started somewhere at the top here, right? And then dropped off. Okay, let me see if I can get as close as possible to this. All right, if your gain is equal to 1,000, then log of your gain will be log of 1,000 is equal to 3. So I see 1.5, I see 2, I see 2.5. 3 will be somewhere at the top here. Let's just use our imagination. All right, so gain will be somewhere at the top here, it will be flat out. And let's say it starts to drop at the same point. It starts to drop right here and it goes down. How will I get my bandwidth? My bandwidth will actually be, if my gain is 1,000, my bandwidth will be, my AV over root 2 will be 707, right? Log of 707 will give me 2.8 or something. Nothing. I get 2.8 in truth. All right, so 2.8 will be somewhere here. My bandwidth, let's read and see across, folks. My bandwidth will actually get, is my bandwidth smaller or larger at a bigger frequency, at a bigger gain? Look and see. Tell me what you're getting. My bandwidth will be from here to here. Will I have a bigger bandwidth at a higher gain, or will I have a smaller bandwidth at a higher gain?
Smaller.
Smaller, right? Because look here, this is your original gain. Our original bandwidth went straight across here. And this is using the same, almost same curve coming down. They came down at the same rate and whatnot to end up at the same spot at the bottom here. So it dropped off at, at the same point. So if this is where you use a little bit of imagination. And this is a note you all can write in your notes. All right? When your gain increases, an increase in gain equals to a decrease in bandwidth. So you would have seen that you had an increase in your gain and thus given us a decrease in bandwidth. It was no sort of calculations beside us to work out your gain again. Right? Yes, I worked out the AV over root 2 pretty quick because there's an easy, simple way to do it. Maths people, if you all want to follow, right? If you know how to work with your surds properly. But this is to tell everybody. Remember, I have to cover everybody bases. All right, 1 over root 2 is equal to 0.707. So if I want to find my 1 over root 2 of anything, I just multiply by 0.707. And 1,000 by 0.707 is 707. So that's how I knew that my root mean gain was 707. And if I wanted to find where it was on this scale, I had to now go and find log of 707, all right, which gave me 2.8 something. All right, and you read across and you find where it intercepted your curve. Just use a bit of imagination, a little bit of extrapolation, and you would have gotten your value. All right, so it's there on the video, so you all can write it back down. I do suggest you all try the question, just writing it down, so you see how fast this can be done. Because this would not have taken more than 10 minutes to do this question. All right, so question 2. How much was this? 10 marks. Yeah, that would have taken about 10 minutes too. Question 2. I have an OpAmp connected to another OpAmp. They're both running. Let's read our circuit. All right, it's not meant to be scary. Well, I hope it's not meant to be scary. Let's read. We have both of our OpAmps are working at plus and minus 6 volts. We have our first amplifier circuit, and then we have our second amplifier circuit. All right, so we can take our first VI as first VI is 0.3, and in this case you can see that the VO of your first circuit or your circuit A is going to be equal to your VI of your second circuit amplifier B. You all can see that, right? Because what we did, we fed in 0.3 volts into our amplifier. That output voltage was now fed into another amplifier to give us a new V out. So in this case, there's an intermediary voltage supply, and that voltage supply is being provided by our amplifier. So continue reading our graph, or continue, not graph, our diagram. So we have our input resistor of our first amplifier, which is amplifier A. Let's look at amplifier A to start with. Our feedback resistor will be 50 kilo ohms. Automatically, we could already work out our gain. 50 divided by 10. We know our gain in our first circuit is going to be 5. Easy peasy. All right, even in the second one, we could work out our gain quick. All right, if we have our input resistor for our second circuit, which is circuit B, is 150, and our output resistor or feedback resistor is 300 kilo ohms. Somebody quickly do some mental maths. What is the gain of the second circuit? Second circuit is in blue. What is the gain of this circuit using just its amplifier? Its amplifier circuit, my apologies. Folks, you could do that mentally.
We are divide R4 over R3.
That's not telling me a value, you know.
Well, if you do that, then you get what, 2?
2. As I said, it's real easy. You could do it mentally.
Oh wait, I thought 2 was wrong.
And I said it really easy. You could do it mentally. This is why I said, you see, for OpAmp questions, they're not necessarily, maths is not hard, but you have to learn to pay attention to what you have around you. We didn't know sort of big maths beyond form, you know, if you knew how to do logs in form 3, that's it. Right. Alrighty, look, I just work out the entire question 1, part 1. I didn't even look at that. So write down the formula for gain of each of the amplifiers, which are cascaded in the diagram above. So the gain for circuit 1, circuit A will be oh, it is not 5. I did a oopsie, y'all. Whoops. My apologies. What type of circuit is circuit A? What type of amplifier? This is circuit A. Let's zoom in, right? What type of circuit is this? Where is my input going into? Circuit A, the lilac marker. Where is my active input going into? What type of input is it going into? Anybody? I'll continue joining.
But I guess since I'm saying V in, that's where the input going in.
So what kind of circuit, what kind of amplifier is this? We only have two types of amplifiers,
Wait, I feel madam.
Anybody else?
Andy have more.
Non-inverted.
Thank you, Andy. This is a non-inverting amplifier, right? And the gain for non-inverting amplifier, why is this a non-inverting amplifier? Because let's track our signal, right? We have grounded our inverting input. So that means this is not an inverting amplifier. If you look here, that our 3.3 volts is going into our positive input, which is our non-inverting input. So this means we have a non-inverting amplifier, and the non-inverting amplifier gain is given by, folks, tell me. I will write out the formula by dots before they say it, What is the gain for non-inverting amplifier? Look in your notes fast. Are we waiting? Anybody else? What is the gain of a non-inverting amplifier? I will draw on the screen while I wait. And you all know I could draw forever. Anyone? Can you please look back at your notes for a topic we've been doing since the start of the term? Well, for the last 4 weeks. What is the gain of a non-inverting amplifier? Rashad, what's the gain of a non-inverting amplifier? Tristan, gain, non-inverting amplifier. Tell me. Anyone? All right, let me wrap up the recording right here because this is now lunchtime. All right, and I do suggest that you all at least read up something. You did have this. Let me just stop the recording.